Hi and welcome to this new video. We will continue with the transient response of first order circuits. This is our ninth example already, example 9. So what we have is that we have a RC circuit with a switch, and in this case we have two independent sources. This is actually different than the previous examples. We only had one independent source, so this is actually a different example. Two independent sources, VM and the IP, and there are also two resistors, R1 and R2, and there is a capacitor given. The values are given here. There is also, in addition, the capacitor voltage at 0, which is 3 volts. So we will use this information also. The question is exactly the same as before. So we need the capacitor voltage as a function of time for t larger than 0. So Vc as a function of time. Now we follow the same procedure as we did in the previous examples. So let's start. How do we start? So we'll look at the situation before the switch closes, so actually for time less than 0. What we have is actually, if you look at the situation when the switch is still open, so there's no change, the situation is actually that this circuit, this part, is disconnected from the capacitor. So the capacitor voltage is actually something if there is no information about it, so you might not know that, but this is already given in the information on the right side. So what you see is the capacitor voltage at 0 is 3 volts. So this is actually the initial value of the capacitor. So this, what we should do, drawing a new circuit, what we already did in the previous examples, is already given to us here. So that's actually the situation. So what we can say is the capacitor voltage at 0 is 3 volts. So this is the initial value. So the initial value of the capacitor voltage. So that's actually the first step. So the next step is looking at the situation when the switch is closed. But what we already said and always do is we don't look at the situation when the switch just closes and then the transient effects. No, we will wait again a long time such that the circuit is in steady state, and we will look at the open circuit voltage of the capacitor. So we will redraw this situation when the switch is closed, and we will model the capacitor as an open circuit. So I will do that, and we will work on that. So what we have is that we have the VM, which is connected to the resistor R1, and then the independent current source IP connected in series with the R2, and then connected to the capacitor, which is now modeled as an open circuit. So I will emphasize this, and this is actually the situation for calculating the final value of the capacitor. So Vc infinity. All right, so what is this actually? I will also denote this point as x to illustrate the situation, and I will make the current flowing through this branch as I1. Okay, so what we can say is the situation for the following. Because this is an open circuit, we can say that there is actually one voltage loop here on the left side of the circuit. The current already in this branch is determined by the IP, so that is non-negotiable. So if you know the current through this branch, and since this is an open circuit, the current must come from this side. So actually we're having a current loop in this fashion. So I can set up the voltage law of the Kirchhoff like Vm is equal to the voltage across R1, which is I1 times R1 plus the voltage at point X. The situation is now very interesting because the I1 is also IP. So because it's in series, so I1 is IP, so it's series. So that means I1 is IP is equal to, which is given there, is 2 milliamps. So if I fill in what is given above, and I know this is the situation for infinity, so the situation when everything is settled, everything is in steady state, then I can write down the equation. 12 is equal to 0.002 times 4,000, 4 kilo ohms, plus the Vx. And why we are interested in the voltage Vx? What is the interesting part of that? The Vx, that node, is actually the same capacitor voltage. So if I know this, then I will also determine the final value of the capacitor. So I will carry out the calculations. 12 is equal to 8 plus Vx at infinity. So this will be Vx at infinity is 4 volts. And like I said, for this case, the capacitor voltage at infinity is equal to the point x at infinity, and that's also 4 volts. So this is actually our steady state value, or the final value. That's actually the second step. Now we have to be very careful and look at the situation for the next and the final step is the time constant. How do we determine the time constant? We will look at the situation when the switch is closed, so there is already a change made, and again we will look at the situation when everything is settled and there are no transient. And we will, in addition, disable all independent sources. So in this case we will look actually to this circuit, and we will disable the IP and we will disable the VM. Now, disabling these sources means the voltage source will be a short and the current sources will be an open. So if I look to the time constant, so if I write down the time constant here, time constant, what I have is actually I will look to this between these nodes, so that's actually the terminals of the capacitor C, and I will look at the resistance seen by the capacitor. So what we have is, I will redraw it again to emphasize what we see. So we have a short due to the VM, which is turned off. We have the R1 still, but IP will be an open, and there is a resistor R2 which is in series, and there is the connection for the capacitor, and I will place the capacitor in to emphasize there is still a capacitor there. So this is the C, and these two terminals are important for us to determine the Thevenin resistance seen by the capacitor C. So what is the time constant? Time constant is the Thevenin resistance times the capacitor value C. But if you look carefully, this is a very simple situation because it's only R1. Why? Because this is open. So it's actually after the picture. So only what you see is the R1. So R1 is equal to R Thevenin, and R Thevenin will be then 4,000 ohms. So that means R Thevenin is R1, which is 4,000 ohms. Then the tau can be calculated like 4,000 times 1 microfarad, so 10 to the power minus 6, that will be 0.004 seconds or 4 milliseconds. Okay, that's actually the third part for our calculation to determine the voltage across the capacitor as a function of time. So we have 3 parameters: the initial value, the steady state value or the final value, and the tau, the time constant. So I can now fill in my formula, so which is V capacitor is V capacitor at infinity, and in parentheses V capacitor initially, V capacitor final times e to the power minus t divided by tau. So let's fill in what we have calculated. So what we see at infinity, or the final value, is 4 plus, this is 3 minus 4 times e to the power minus t divided by 0.004. So I can simplify this a little bit to see the formula easily. So that is 4 minus e to the power minus 250 t, and this will be in volts. That's actually the situation what we have here. So if you want, you can also again calculate the current. That's actually not required in the question, but that is actually very easily carried out using the formula we already discussed in the previous examples. So that's actually the situation here. Maybe we can do that, no problem. Let's do this is the voltage, so that is the capacitor. So that is the capacitor voltage. And that is the capacitor current. So let's do that also. That might give us more insight in the problem. So what's the capacitor current? Capacitor current IC is equal to C times the derivative of the capacitor voltage. Since we know the capacitor voltage already, this is actually very straightforward, and it is a very short calculation. So what we have is C is 10 to the power minus 6 times the derivative of the expression we have here. That's 4 minus e to the power minus 250 t, and then carry out the calculation, do the math. What you get is, let's put also the t in parentheses. What you get is 10 to the power minus 6, and then differentiate this expression. What you get is minus 250 times 250, minus 1 I mean, so you get 250. So what you get is 250 e to the power minus 250 t, and if you simplify this further, you get 250 times 10 to the minus 6, or you want to write it down in micros. So what you get is e to the power minus 250 t microamps. That's actually the situation for this part. Okay, so that's for the current. For the capacitor voltage we have this, and for the capacitor current we have this. Let's draw also the graph for both of them. That will also give us a lot of insight. So let's do that. So this is the y-axis. So this is the x. So this is the time, and this is the voltage, which is in volts. And that's the current also at the same axis as a function of time, but in microamps. Okay, what we have is, let's start here at 0 and then make this also 0, and I will denote in red the voltage. So actually what you see is, you start at the time equals 0 at 3 volts. So that's actually what's already given, so that's 3 volts. So you start at 3 volts. And when the time moves on, so then this part will disappear. So you will actually grow to 4 volts. That's actually what you have. So you will level off at 4 volts. So what you have is actually this curve for the first order expression. So this is VC. How about the current? Now the current, what you can see is at time equals 0, it is 0. This is, no, not 0, excuse me, 250 microamps. So you start at 250 microamps, and you will, and this will reduce to 0 when time goes to infinity. So actually, this is of course two axes in one place. So you have to be very careful to how to read this. So this is 250. So blue line is different than the red line, and it will reduce to 0 amps. And I will try to make this clear. Okay, and this blue line is the current. So this is the current through the capacitor. And then we have the full picture actually. What you see is the voltage is growing and leveling off at 4 volts, and the current, which starts at 250 microamps, will reach again 0 at a specific time. You might say, how long does it take to reach the 0 and how long does it take to reach the 4 volts? That is actually determined by the time constant. That's actually why it's called time constant. So in engineering we use 5 time constants to say, okay, we have reached our final value, so this will also reach the final value after 5 time constants, and this will also reach the final value after 5 time constants. So what is 5 time constants in this case? Now we have the tau of 4 milliseconds, so the final value, which is around here, will be about 4 milliseconds times 5, so about 10 to 20 milliseconds. So about 20 milliseconds, maybe a little bit more, you will reach approximately the final value of the voltage and also of the current. So we will again, of course, continue with the other examples. I hope this is very helpful also in drawing a circle, drawing the graph. Might give you a lot of insight in the situation about transient response. This is actually, if you understand the situation, not really difficult. Just follow the steps very carefully, but and also redraw the circuit when you feel you might miss something. Okay, good luck with the study, and I will see you next time.